Okay, so welcome back to the second session. We start with BKO on star formation beyond redshift 0.
All right. Hi, everyone. I'm Boon Kiat, or BK in short, and it's great to be here. Thank the organizers for this chance to talk about my work. And we're going to switch gear and we're going to look at star formation, but not in the past, but into the future, and how it's going to affect our analysis of the cosmological constant. So this work is done with my collaborators from University of Edinburgh, as well as collaborators from SNU. So, all right, we're all familiar with the composition of the universe, much of it that we can't see, and we can only see 0.5% of it, but we can use this 0.5% to tell us a lot about the dark sector, so the dark energy and dark matter, as a lot of presenters have already talked about. So let's look at the cosmological constant, the dark energy section. It's introduced by Einstein in his model in 1917. So he used this to have a static model of the universe. So when Hubble's observation in 1929 showed it's expanding, he quickly abandoned it, and from that point on, we have Einstein de Sitter models and loitering models that's being proposed to explain this expansion. But in the end, lambda triumphed, and it stayed in the cosmological model and because of combination of several observations. However, its position in the cosmological model is not unquestioned. So, right, the problem is with the value of the rho vacuum that we see. So if we approach it from a theoretical point of view, starting with the 0-point energy, and if we were to sum this all up for all the normal modes of the quantum field, and believing GR to Planck scale, this rho vacuum turns out to be 10 to the 92 kilograms per meter cube. But if you look at observations, this rho vacuum is actually 10 to the minus 26. So there's 120 orders of magnitude in this problem of the cosmological constant. So what we can use to explain this difference is the entropic principle. So essentially what it means is the universe is in its state because we as observers are here to observe it. So there's the weak variation as well as the strong variation, but that's the main idea. So this principle has been used by Weinberg in 1987 to argue that lambda cannot be extremely positive nor extremely negative. So if it's extremely positive, then the expansion will be too fast before any meaningful structure formation can happen. And if it's extremely negative, then the recollapse of the universe would also inhibit any structure formation. So we are trying to link this with observers. So obviously, the way that we can do this is the cosmic star formation history using stars. Let's maybe replace this with the CGM figure. So we start with the Maddow and Dickinson Maddow plot. So they have this cosmic peak in around redshift 2, and it climbs exponentially to redshift 0. So there's a functional form that we fit. But the question is what happens into the future. So this is important because if this decrease is to continue into the future, it means that in our universe there's a finite amount of stars that can be produced, and that means there's a finite probability for observers to exist. But of course there's also a chance for it to turn around, and that's what people with Eagle simulation have done in 2018. So you see here, it's the lambda CDM where they run it with the Eagle prescription. So if you were to run it into the future, beyond redshift 0, you find that the cosmic star formation rate continues to decline. However, they also find that if you were to switch off the AGN feedback, you can actually have a turnaround in the star formation rate. So having a turnaround in the star formation rate, it means that the stellar mass in our universe would not be finite. However, there's an issue, or we would like to propose an improvement on this simulation. So the simulation actually ended around 20 gigayears, which is not even at the point of freeze out. So freeze out is, you see here the growth factor against the age of the universe. So you see the freeze out occurs around 30 gigayears, where basically the halos would no longer have interactions with each other and they will only evolve in isolation. And of course, there's the chance of further star formation, because if you go to infinite time, there's infinite time to cool, and because your star formation is already declining, there's a reservoir of cold gas that's available. So what we want to do is to associate observers with stars. And to do this, we run simulations into the future and as well as counterfactual universes. So to have the entropic weights that we want to use to explain the value of the cosmological constant. So the tools that we use is, so we have generating initial conditions right up to the chemistry as well as the analysis. So these are all the tools that we use for the simulation. And of course, to run simulations, we have to calibrate the simulations to something. So we use the observations from McGaw et al. In 2010. They have this FD and FS parameter according to the mass. So the FD is basically just the baryon mass within a certain halo mass, and the F star is the M star. So this is important because we want the halos by redshift 0 have the right composition of stars as well as gas, so that we can evolve it into the future. And this is the result of the calibration. So you see, we managed to get not just the main halo in our simulation, but because this is a zoom-in simulation, we have other halos in the mass refined region, and we managed to get quite a good fit for the FS and the FD. So with this, we are confident that our halos at redshift 0 should contain approximately the right amount of stars and gas for it to evolve realistically into the future. So this calibration was done by me. It's done manually, and we tune just 3 parameters: the star formation efficiency, so the conversion efficiency from the gas to stars, the efficiency of the feedback, and the energy in which the feedback is being injected into. So this plot here you see on the FS against FD plane, we change parameters individually, and it took a total of 71 simulations. So this was done in 2020, and during my time at SNU, we did this using machine learning. So what we did is we want the same calibration, but now instead of doing it manually, we ask the machine to do it. So we provide the machine with simulation training data, so just 5 initial training data to the machine. And we ask the machine at each point to suggest a set of parameters for us to run, to test, in order to match the observation of the FD and FS. So this here is the difference between the simulated and the observed. So the machine actually did it much faster than manual calibration. So we found this using only 22 simulation. It's a factor of 3 in savings in computational resources. And it's actually, the agreement is actually much better than those that's being found manually. So once we've done this, we want to look at the star formation rate. So we did this by varying some of the parameters, the resolution in the simulation. So NL is the fiducial resolution that we're using. -1, +1 is decreasing and increasing the spatial resolution. And with M in front, it's just changing the mass resolution. So what we found is that, the black line, solid and dashed line is the one from observations. So what we found is that if we have better mass resolution, we can have earlier star formation. So that's just because our structure formation will begin earlier. But the interesting point here is at this point, we can actually see a turnaround in star formation in our own simulation. So every single simulation has a turnaround except the one in red, which has the best spatial resolution. So this tells us that this turnaround is actually due to the resolution effect and not due to the physical effects that's happening. But as I said, we are interested in, so now that we've established that the turnaround is not physical, we are interested in the amount of total stellar mass that we can form. So you see, again, based on the convergence, we can have a finite mass that's derived from observation, and you can see those the simulations that we run, even with just the fiducial, is close to what we have from observation. So this is the next piece of the puzzle. We have the realistic evolution up to redshift 0. Now we can go beyond redshift 0 in lambda CDM to show that we can have a good agreement in the total stellar mass that's being produced. So the last step is to go to different cosmology. So this here shows how the different parameters should vary as we change it. So the dots are just the fiducial lambda CDM that we're using. So we have to, in each simulation, we have to change the box size and the starting redshift because we are changing the entire cosmological parameters. So we ran one set to change the value of lambda, and we ran another set of simulations to modify sigma 8 just to mimic the effect of changing lambda. So what we see here is the star formation efficiency, the evolution of the cosmic star formation rate in different universes. So Einstein disturb, lambda CDM 10 times lambda, 50 times 100, and so on and so forth. So these are with prefix of S is changing the sigma 8. So you can see actually all of them follow the same functional form for the plot, for the fit that Madhav and Dickinson have. So we generalize it, and yeah, so these are all the plots these are all the fits that you can see to all the data points in different cosmology. So what this means is that there's also a finite amount of stellar mass that we can extract from different cosmology. And dividing it by the amount of baryon mass that's available, we are able to give the entropic weights to universes of different values of lambda. So this red line is the one where we scale the value of lambda. This purple line is sigma 8. You can see that sigma 8 is very different from the rest. So FC is the collapse fraction done by Peacock in 2007. So he looked at the fraction of baryon mass in the universe that would collapse into halos of a critical mass near the Milky Way. So you can see that, so again, the blue line is the fits to Barnes. So Barnes et al. Is using they are using the ego simulation to probe this idea of the multiverse. So what we have is a comparison. We can see that when we scale sigma 8, the values are actually very different. So we'll just focus on changing lambda. And all right, so they can all, again, they can all be fitted with the same functional form. And with this, we can draw the relative probability of the entropic weight. So we can see, so the data that we have from Peacock 2007 shows approximately 8.2% of observers actually live in universes similar to ours. And using our own suite of simulation, we predict a higher percentage. So it's more probable that our universe would exist as compared to Barnes et al. So the blue line you see here, they tend to favor higher values of lambda. But the main point here is that we are pushing simulation codes into regimes that they are not familiar with. So going into the future where the expansion is rapid and as well as low density. So because in our own simulation, we had to make changes to the publicly available version as well. So we are saying that the galaxy formation modeling is actually robust and can help us predict the values of lambda that we want to see. So the conclusion is that we push the simulation codes beyond their familiar regime, and we find that there's a decline in the star formation rate beyond our present time. There's also an improvement in the applicability of the entropic argument, but it's not perfect yet, likely because the the entropic weight is not perfect, it's just simply stellar mass weighted. If you were to consider planet formation, where we have to take into account the metallicity, that might give us an even better estimate. And of course, using black hole physics, especially in Einstein de Sitter, so structure formation is supposed to be highly effective in the Einstein de Sitter universe, so we didn't include this. And lastly, we only considered half of the probability, so we only focus on the values of lambda that's positive. There's an entire range of universes that exist that has the negative cosmological constant. So if you were to include all of this, we might be able to get a better constraint on the probability of observers existing in universes like ours. Yeah, that's the end. Thank you.
Okay, Nir?
In all of your experiments, did you always assume the universe was flat?
Yes.
Yes. What about assuming that it's not flat as well? I mean, if you're already assuming a negative lambda, why not assume non-flat as well?
Yeah, that's also a possibility. Yes, there's a lot of extension that can be done. Yeah.
Okay, anyone? Yep. David?
I was wondering whether it's possible to include other constraints like, well, we see the universe with a certain visible horizon. And so if you say, what's the chance of creatures being able to see the universe that's very large versus that which would be very small? I assume that 30 billion years from now at the current lambda, that the visible universe could be very, very tiny, right? And so that may not be a sort of a viable universe, because there must be somewhere you don't even see any, can't even get enough to get star formation that was viable for the production of life. That can see the universe. Close, along the anthropic, but putting constraint about the size of the visible universe. Is that something of value in your studies?
Yes, actually, yes. It definitely depends on the size of the observable universe. So, like, for example, the Barnes et al. That I talked about, where they use the Eagle simulation, they have these different constraints on the size of the universe that they actually use to weigh this. So, again, in the comparison that I made, it's only with the simplest, just infinite, and that's stellar mass weighted. So they are like they have this thing called the causal patch as well that they use. So it gives a constraint on the area, the volume that you have of the universe.
Okay, so I don't think there are any more questions. Let's thank BK again.
Thank you.